Now let's have the discussion on star delta connection. And here the assumption is primary is HV and secondary side is LV winding. Therefore, now let's consider the bank of 3 single phase transformers and let's give the dot notations. And as these 3 are the HV side winding, so the notations will be in capital letters and the dotted end terminals are A2, B2 and C2, and the non-dot ends on primary side are A1, B1 and C1. And now on secondary side this is LV winding, so the notations will be in smaller case and the dot ends are small a2, small b2 and small c2, and the non-dot ends are given a1, b1 and c1. So now as we are studying the case of delta star connection, means the primary side windings are connected in delta and secondary side windings are connected in star. So now first let's connect the primary side windings in delta, and to obtain the delta connection we are joining the non-dot end terminals of one coil with the dot end terminals of other coil, or we are joining the dot end terminals of one coil with non-dot end terminal of other coil. And here we are joining the non-dot terminal of one coil with dot end terminal of other coil, non-dot end of one coil with dot end terminal of other coil, and similarly non-dot terminal of this coil is connected to dot end terminal of other coil. And here we are taking the connections from dot ends, that is capital A2, capital B2 and capital C2 on primary side. And now coming to the secondary side winding, that is LV winding. Here we are having star connection, and star connection is obtained by joining the dot end terminals of all the 3 coils together and taking the connection from other ends of the coils. So here the common ends could be non-dot end terminals or dot end terminals, and here we are considering the common end terminal as non-dot ends. So let's join the non-dot ends together. So small a1, small b1 and small c1, and take the connections from dot end terminals. So small a2, small b2 and small c2. So this is the one of the possible connection of delta star connection. We are having 4 possible connections of delta star connection, that is we can obtain delta star connection in 4 ways. So this is one of the way, and now we are going to draw the phasor diagram for this type of connection. So for that, let's arrange these windings in horizontal fashion. Let these 3 be the HV windings and let these 3 be the LV windings. These be the dot end terminals. Now let's give the notations. So as these 3 are the HV winding connections, so the notations will be in capital letters. So dot end terminals are A2, B2 and C2, and non-dot end terminals A1, B1 and C1. Now coming to the LV winding, so notations are in smaller case, that is small a2, small b2 and small c2, and non-dot end terminals small a1, small b1 and small c1. Now as HV winding is connected in delta, and to obtain delta we join the non-dot end terminals with dot end terminal. So join the non-dot terminal with dot end terminal, non-dot terminal of one coil with dot end terminal of other coil, and non-dot end terminal with dot end terminal, and taking the connections from dot end terminals, that is capital A2, capital B2 and capital C2. And now coming to the second side, that is LV winding. It is star connected, and this star connection is obtained by joining the non-dot end terminals to a common point and taking the connections from dot end terminals. So let's join the non-dot end terminals small a1, small b1 and small c1 together and take the connections from dot end terminals small a2, small b2 and small c2. This is how we arrange the HV winding and LV winding in horizontal fashion. Now we have to draw the phasor diagrams for this HV winding and LV winding. So first let's draw the phasor diagram for HV winding. So as HV winding is delta connected, that is as primary winding is delta connected, let's take this as VA phasor, and now we need to decide the terminals of primary side VA phasor, as the terminals are A1 and A2, and we are taking the connection from dot and terminal, that is A2. So arrow will point towards the dot and terminal, that is A2. So other end will be A1. Okay, and to A1 B2 is connected. So here we will have B2 terminal. Now let's draw the VB phasor, and we know that for ABC phase sequence in three-phase system, if VA is at an angle 0 degrees, that is VA is taken as reference, then VB will be at an angle minus 120 degrees and VC will be at an angle minus 240 degrees from VA. Therefore, VB will be at an angle minus 120 degrees from VA. So, as VA phasor is like this, so from this phasor at an angle minus 120 degrees, that is in clockwise direction, because minus 120 degrees, there will be VB phasor. So, VB phasor will be along this direction. Let's draw the VB phasor somewhere here. And now let's decide the terminals of primary side VB phasor. As the connection is took from dot and terminal, that is B2. So arrow will point towards B2 terminal. Therefore, other end will be B1. So as A1 is having B2 terminal, therefore draw this phasor like this such that A1 will have B2. So this is VB phasor and other end will be B1. Now let's draw the VC phasor, which will be at an angle minus 240 degrees from VA, or we can say that VC will be at an angle minus 120 degrees from VB. So as this is VB, so from here in clockwise direction at an angle minus 120 degrees, there will be VC like this. So let's consider the VC phasor like this somewhere here. And now let's decide the terminals of primary side VC phasor. And here on primary side we are taking the connections from dot and terminals. So that is here C2. Therefore arrow will point towards dot and terminal, that is C2. And other end will be C1. And now observing winding connection that to B1 there will be C2 connection. Means in phasor diagram to B1 there will be C2 point. Therefore draw this VC phasor such that B1 will have C2 terminal, and therefore this will be C1. So this is how the phasor diagram for delta connection is obtained. But here there is one more important point that to be discussed, that is here in delta connection we must consider the imaginary neutral, and we know that in delta connection there will be no neutral connection, but for reference purpose or for comparison purpose we need to take the neutral connection, because the numerical in vector group symbol will indicate the LV winding phase to neutral voltage displacement with respect to HV winding phase to neutral voltage. Therefore, we need the LV side phase to neutral voltage and HV side phase to neutral voltage. So, as in delta connection there is no neutral connection, therefore we must take the imaginary neutral. Now let's draw the phasor diagram for LV winding on secondary side. So, as this is star connected, and we know that secondary side phasors are drawn parallel to primary side phasors. First, let's draw the secondary side VA phasor parallel to primary side VA phasor. So, if this is the secondary side VA phasor parallel to primary side VA phasor, now we need to decide the direction. So, direction depends on the connection we took on primary side and secondary side. So, as the connection on primary side and secondary side are took from dot and terminals, therefore secondary side phasor direction will be same to that of primary side phasor. So the direction will be same, that is like this. And now we need to decide the terminals of secondary side VA phasor. As the connection is took on dot and terminals, therefore arrow will point towards the dot and terminal, that is A2, and the other end will be A1. Now let's draw the secondary side VB phasor. So let's draw the secondary side VB phasor parallel to primary side VB phasor somewhere here like this, and on primary side and secondary side connections are took on dot ends. Therefore the secondary side VB phasor direction will be same to that of primary side VB phasor. And now we need to decide the terminals of VB phasor, and as the connections are took on dot and terminals, therefore arrow will point towards the dot and terminal. Therefore this will be B2 and the other end will be B1. And observing winding connection that to A1 there is B1 connection. So here to A1 there will be B1. So now place this phasor such that A1 is having B1 terminal. Therefore, this will be the VB phasor. Now let's draw the secondary side VC phasor. So drawing the secondary side VC phasor parallel to primary side VC phasor. And now let's decide the direction of secondary side VC phasor. As the connections on primary side and secondary side are took on dot ends, therefore secondary side VC phasor direction will be same to that of primary side VC phasor. So like this. And now let's decide the secondary side VC phasor terminals. As the connection is took on dot end, therefore arrow will point towards dot end terminal, that is here C2, and the other end will be C1. And observing winding connection that to A1, B1, C1 has connection. So to A1 and B1 there will be C1. So now draw this secondary side VC phasor such that it will have C1 here. So this is the phasor diagram for this type of delta star connection. And now let's identify the vector group symbol for this type of delta star connection. And we know that the first character in vector group symbol is in capital letter, and that will indicate the HV winding connection. And here the HV winding connection is delta, so it is represented with capital D. And now the second character in vector group symbol is in smaller case, and that will indicate the LV winding connection. So here the LV winding connection is star. So to represent that, the second character is in smaller y. And the third position of vector group symbol is a numerical, and that numerical will indicate the LV winding phase to neutral voltage displacement with respect to HV winding phase to neutral voltage, and that is obtained from clock notation. So now come to the phasor diagram and observe that the HV winding phasor diagram is delta connected. So here the phase to neutral voltage is A to N, and from the LV winding phasor diagram the phase to neutral voltage we are taking is small a to N. Okay, we are considering the common N terminal as small n here. So phase to neutral voltage here is small a to N. And now superimpose this diagram on this diagram and observe the phase to neutral voltages of HV winding and LV winding. So if you superimpose, then HV winding phase to neutral voltage will look like this, and LV winding phase to neutral voltage will be like this. And in clock, this HV side phase to neutral voltage is represented with minutes needle, and as HV side phase to neutral voltage is taken as reference, so minutes needle is always shown pointing towards 12. If suppose this is the clock, and as the HV winding phase to neutral voltage is represented with minutes needle, and as it is taken as reference, so minutes needle is always shown pointing towards 12, and the LV winding phase to neutral voltage is represented with hours needle in clock. So now place this diagram in clocks such that the HV winding phase to neutral voltage will point towards the 12. Then the diagram will look like this. So now the secondary side phase to neutral voltage will point towards 11, means the numerical in vector group symbol here is 11 because this represents 11 o'clock, and which will indicate the LV winding phase to neutral voltage displacement with respect to HV winding phase to neutral voltage, and that is given by the angle between the minutes needle and hours needle in clock. And here the angle between minutes needle and hours needle is 30 degrees, and as the angle is measured anti-clockwise, so it is given positive sign. Therefore, for this type of delta star connection, we are getting a phase displacement of plus 30 degrees. That is, here with this connection we are having 30 degrees lead phase displacement. Now let's draw the second possible connection of delta star connection. In that, what we are doing means we are leaving the primary side connection as it is, and the change we are making here is on secondary side. That is, instead of joining the common terminals A1, B1 and C1, we are joining the common terminals A2, B2, C2 and taking the connection from non-dot ends. In this case, we took the connections from dot end terminals, and now in the second possible case, we are taking the connections from non-dot ends. Now let's see that. Therefore, in second possible connection of delta star connection, here we are joining the dot end terminals together and taking the connections from non-dot ends on secondary side, that is on LV side. As we left the HV winding connection as it is, so the phasor diagram will be same. Now let's draw the phasor diagram for LV winding connection, and it is known that the secondary side phasors are drawn parallel to primary side phasors. So let's draw the secondary side VA phasor parallel to primary side VA phasor. And now let's decide the direction of secondary side VA phasor, and that direction depends on the connections we took from the primary side and secondary side. Therefore, observe that on primary side connections are took from dot end terminals, and on secondary side connections are took from non-dot end terminals. Therefore, the direction of secondary side VA phasor will be in opposite direction to primary side VA phasor. Therefore, the direction will be like this. Now, let's decide the terminals of secondary side VA phasor. And here in winding connection, observe that the connection is took from non-dot end terminal, that is A1, as arrow will point towards the connection we took from. Therefore, the terminal here is A1, the other end will be A2. Now let's draw the secondary side VB phasor. So let's draw the secondary side VB phasor somewhere here parallel to primary side VB phasor. And now let's decide the direction of secondary side VB phasor. So here on primary side connections are took on dot end, and on secondary side the connections are took on non-dot end. Therefore, secondary side VB phasor direction will be opposite to primary side VB phasor. Therefore, the direction will be like this. Now let's decide the terminals of secondary side VB phasor. So as the connections are took from non-dot end terminals, therefore arrow will point towards the connection we took from, that is here B1. Therefore, the other end will be B2. And observing winding connection that to A2 terminal there is B2. Therefore, to A2 we will have B2 connection. So draw this secondary side VB phasor such that the A2 terminal will have B2 like this. Now let's draw the secondary side VC phasor. So let's draw the secondary side VC phasor parallel to primary side VC phasor somewhere here like this. And now we need to decide the direction, and here on primary side connections are took from dot end terminal, and on secondary side connections are took from non-dot end terminal. Therefore, secondary side VC phasor direction will be opposite to primary side VC phasor. So the secondary side VC phasor direction will be like this. Now we need to decide the terminals of secondary side VC phasor, and here the connections are took from non-dot end terminals, that is C1. Therefore, arrow will point towards C1. The other end will be C2. And observing winding connection that to A2 and B2 there is C2 connection. So here there will be C2. Now draw the secondary side VC phasor such that here it will have C2 connection. So draw as it is the secondary side VC phasor. And let's give the common notation to this common connection. So let this be small n, as this is LV winding. Now let's identify the vector group symbol for this connection. As we know that the first character in vector group symbol is in capital letter, and that will indicate the HV winding connection. So as the HV winding connection is delta, to represent that it is taken in capital D. And the second character in vector group symbol is in smaller case, and that will represent the LV winding connection. And here the LV winding connection is star, and to represent that small y. And now we need to decide the third portion of vector group symbol, which is a numerical, and that you can obtain by observing these phasor diagrams. And that numerical will indicate the LV side phase to neutral voltage displacement with respect to HV side phase to neutral voltage. Therefore, we need the LV winding phase to neutral voltage and HV winding phase to neutral voltage. From HV winding phasor diagram, capital A to N is the phase to neutral voltage, and this is taken as a reference, and this is indicated by minutes needle in clock. And as this is taken as a reference, the minutes needle in clock is always shown pointed towards 12. So if you take this clock, and this is the minutes needle which is shown always pointed towards 12. And coming to the secondary side phasor diagram, A1N is the phase to neutral voltage, and LV side phase to neutral voltage is represented with hours needle in clock. Therefore, first let's superimpose this diagram on this diagram and observe the phase to neutral voltage of HV winding and LV winding. So if you superimpose HV winding phase to neutral voltage and LV winding phase to neutral voltage will look like this. And now if you place this diagram in clock such that the phase to neutral voltage will point towards 12, then the diagram will look like this. So hours needle will be pointing towards 5, which will indicate 5 o'clock, and from this we can say that the numerical in vector symbol is 5, and which will indicate the LV side phase to neutral voltage displacement with respect to HV side phase to neutral voltage, and that is given by the angle between minutes needle and hours needle. And if you measure in anti-clockwise direction, this will be minus 150 degrees, or if you measure in anti-clockwise direction, that will be 210 degrees. Therefore, from first possible connection we got a phase displacement of plus 30 degrees, and with second possible connection we got a phase displacement of 210 degrees. Now let's draw the third possible connection of delta star connection. In third and fourth possible connection of delta star connection, now we will have the changes in HV winding connections. That is, in first and second possible connection we join the non-dot end terminal with dot end, and now in third and fourth possible connection we will join the dot end terminal with non-dot end. This is the only change that we are making in primary side, that is in HV side. And now coming to the LV winding connection, in third possible connection we will join the non-dot end terminals and take the output from dot end terminals, and in fourth possible connection we will join the dot end terminals and we will take the connections from non-dot end terminals. Now let's see the third possible connection of delta star connection. Let these three be the primary side HV windings, and let these three be the secondary side LV windings, and here on primary side we are having delta connection. In first two possible connections we join the non-dot end terminal with dot end. Now in coming two cases, that is in third and fourth possible connection, we are joining the dot end terminal with non-dot end, dot end terminal with non-dot end, dot end terminal with non-dot end. So this is the HV winding delta connection. And now coming to the LV winding, which is a star connected, and here we are taking the common connections as A1, B1 and C1. So let's join that and take the connections from A2, B2 and C2. And now let's draw the phase diagram for this connection. First, let's draw the phase diagram for primary side delta connected winding. Let us suppose this is the VA phasor, and now let's decide the terminals of this primary side VA phasor as arrow points towards the connection we took from. So that is here A2, therefore this will be A1. Now observe in primary side winding connection that to A2 there is B1 connection and to A1 there is C2 connection, and we know that in three-phase ABC phase sequence system, VA will be at an angle 0 degrees and VB will be at an angle minus 120 degrees and VC will be at an angle minus 240 degrees. Therefore, let's draw the VB phasor at an angle minus 120 degrees, okay, from VA. So if this is the VA phasor, now in clockwise direction, because minus 120 degrees, so in clockwise direction at an angle minus 120 degrees there will be VB phasor. So let's consider this as VB phasor, and observing winding connection that on primary side the external connections are took from dot and terminals, therefore arrow must point towards dot and terminal, therefore this must be B2 and other end must be B1. So now place this VB phasor such that this A2 will have B1, therefore VB phasor will be like this. This is B2. And now let's draw the primary side VC phasor, which will be at an angle minus 240 degrees from VA, or we can take at an angle minus 120 degrees from VB. Therefore, as this is the VB phasor, so in clockwise direction at an angle minus 120 degrees, let's draw VC. So VC will be in this direction like this. So let's consider VC like this, and let's give the notation C1 and C2, and observe in primary winding connection that C2 is the terminal from which we are taking the connection. So C2 must have arrow, Therefore, like this. Now observe winding connection that to B2 there is C1 connection, means here we must have C1, and to A1 there is C2 connection, means here C2. Therefore, place this phasor here such that B2 will have C1. Therefore, this is the phasor diagram for delta connection on primary side. And here in delta connection we need to decide the phase to neutral voltage for reference purpose, because it is on HV side, and we know that there will be no neutral connection in delta connection, but for reference purpose we need to consider the neutral connection. So here we are considering the imaginary neutral connection. As this is HV side, let's consider that with capital N. And now we need to decide the of A2N and A1N, which is the phase neutral voltage. So observe in primary winding connection that the external connections are took from A2. Therefore, here the reference phase neutral voltage will be A2N. So this is the phasor diagram for this type of delta connection. Now let's draw the LV winding phasor diagram. And we know that the secondary side phasors are drawn parallel to primary side phasors. So let's draw the secondary side VA phasor parallel to primary side VA phasor. So let this be the secondary side VA phasor parallel to primary side VA phasor. Now let's decide the direction of secondary side VA phasor. So which depends on the connections we took on primary side and secondary side. So observe that on primary side the connections are took on dot and terminals, and on secondary side the connections are took on dot and terminals. Therefore, the secondary side VA phasor direction will be same to that of primary side VA phasor. So like this. Now let's decide the terminals of the secondary side VA phasor. As the connections are took from dot and terminals, that is A2, therefore arrow will point towards A2. So other end will be A1. Now let's draw the secondary side VB phasor. So drawing secondary side VB phasor parallel to primary side VB phasor like this. Now let's decide the direction of secondary side VB phasor. As the connections on primary side and secondary side are took on dot and terminals, therefore secondary side VB phasor direction will be same to the top primary side VB phasor. So like this. Now let's decide the terminals of the secondary side VB phasor. So as the connections are took from dot and terminals, therefore arrow will point towards the B2. So other end will be B1. Now observing winding connection that to A1 there is B1 connection, means to A1 there must be B1. So now draw this secondary side VB phasor such that A1 will have B1 terminal. Therefore this will be B2 and this is B1. Now let's draw the secondary side VC phasor. So let this be the secondary side VC phasor drawn parallel to primary side VC phasor. And now let's decide the direction. So as the connections on both primary side and secondary side took on dot ends, therefore secondary side VC phasor direction will be same to that of primary side VC phasor. So like this. Now let's decide the terminals of this secondary side VC phasor. So as the connections are took from dot and terminals, so arrow will point towards dot and terminal, that is C2. So this is C1. And observing winding connection that to A1 and B1 there is C1 connection, means here we will get C1. So draw this phasor such that A1 and B1 will have C1 terminals. So like this. This is VC phasor and the end will be C2. And now let's give the common notation for this common connection. Let that be small n. Now let's identify the vector group symbol for this type of connection. And it is known that the first character in vector group symbol is in capital letter, and that will indicate the HV winding connection. And here we took the HV winding as delta. So to represent that, the first character in vector group symbol is capital T. And the second character in vector group symbol is in smaller case, and that will indicate the LV winding connection. And here we took the LV winding connection as star. So to represent that, it is represented in small y. And now we need to decide the third position of vector group symbol, which is a numerical, and that numerical is obtained by clock notation. And to obtain that, let's observe these phasor diagrams, because that numerical will indicate the LV winding phase to neutral voltage displacement with respect to HV winding phase to neutral voltage. So we need the LV winding phase to neutral voltage and HV winding phase to neutral voltage. So in star connection, that is in LV winding here, the phase to neutral voltage is small a to n, and on HV winding the phase change neutral voltage is capital A to N, and it is studied that the HV winding phase change neutral voltage is represented with minutes needle in clock and is always taken as a reference, so it is always shown pointing towards clock. And now to know the numerical, let's superimpose this diagram on this diagram and observe the phase change neutral voltage of HV winding and LV winding. So if you superimpose, then HV winding phase change neutral voltage and LV winding phase change neutral voltage will look like this. And it is also studied that the LV winding phase change neutral voltage is represented by hours needle in clock. Okay, so now if you place this diagram in clock such that the HV winding phase change neutral voltage points towards 12, so then the diagram will look like this. So now the hours needle will be shown pointing towards 1, means the numerical in vector group symbol will be 1, which will indicate the LV winding phase change neutral voltage displacement with respect to HV side phase change neutral voltage, and that is obtained by the angle between minutes needle and hours needle. So for 1, the angle between minutes needle and hours needle is 30 degrees, and as this angle is measured in clockwise, so it is given negative sign. From this we can say that with this connection we are obtaining 30 degrees lag phase displacement. Now let's obtain the fourth possible connection of delta star connection, and in that what we are doing means we are leaving this connection as it is, and the change what we are making is here is only on secondary side. So instead of joining the A1 B1 C1, we will join A2 B2 C2 and take the connections from A1 B1 and C1. Now let's see that. In fourth possible connection of delta star connection, what we are making that on secondary side we are joining the dot-end terminals, that is A2, B2 and C2, and taking the connections from non-dot-end terminals, and HV winding connections we left as it is. So the phasor diagram is same. And now let's draw the phasor diagram for LV winding connection. Okay, so the secondary side phasors are drawn parallel to primary side phasors. So let's draw the secondary side VA phasor parallel to primary side VA phasor. So, okay, like this. Now let's decide the direction of secondary side VA phasor, and which depends on the connections we took on primary side and secondary side. So on primary side connections are took from dot ends, and on secondary side connections are took from non-dot ends. Means the secondary side phasor direction will be opposite to primary side VA phasor. So as the primary side VA phasor is upwards like this, therefore the secondary side VA phasor direction will be like this. Now let's decide the terminals of this secondary side VA phasor, and here we are taking the connections from non-dot end terminals, that is A1. Therefore arrow will point towards A1, so other end will be A2. And now let's draw the secondary side VB phasor. So let's draw the secondary side VB phasor parallel to primary side VB phasor somewhere here. And now let's decide the direction, as the connection on primary side is from dot end terminal and the connection from secondary side is from non-dot end. Therefore the direction of secondary side VB phasor will be opposite to primary side VB phasor. So as the primary side VB phasor is towards this direction, so secondary side VB phasor direction will be like this. Now let's decide the terminals of VB phasor, and observe that here the connections are took from non-dot end terminals. Therefore arrow will point towards B1, the other end will be B2, and observe by any connection that A2 is having B2. Therefore to A2 we must have B2. So place this VB phasor such that A2 will have B2 terminal. Therefore the phasor is like this. This is B1. Now let's draw the secondary side BC phasor. Let this be the secondary side BC phasor drawn parallel to primary side BC phasor. Now let's decide the direction of secondary side BC phasor. As on primary side the connections are took from dot ends, and on secondary side the connections are took from non-dot ends. Therefore secondary side VC phasor direction will be opposite to primary side VC phasor. Therefore the direction will be like this. Now let's decide the terminals of VC phasor. So as the connection is took from non-dot end terminal, that is C1, therefore arrow will point towards C1 and the other end will be C2. And observing by any connection that to A2 and B2 there is C2 connection, means here we must get C2. So draw this phasor such that A2 and B2 will have C2. So like this. This is BC phasor which is having C1 term. So now let's identify the vector group symbol for this type of delta star connection. Okay, and we know that the first character in vector group symbol is D because the HV winding connection is delta, and the second character in vector group symbol is small y because the LV winding connection here is star connection. And now we need to design the numerical in vector group symbol for this type of connection. For that, let's superimpose the LV winding phasor diagram on HV winding phasor diagram and observe the HV winding phase node voltage and LV winding phase node voltage. So if you observe that HV winding phase node voltage will be like this and LV winding phase node voltage will look like this, and it is studied that the HV winding phase node voltage is represented with minutes needle in clock, and that is taken as a reference, so it is always shown pointing towards 12, and LV winding phase node voltage is represented with hours needle in clock. Okay, now if you place this diagram such that the HV winding phase node voltage will point towards 12, then the diagram will look like this. Means the hours needle is shown pointed towards 7, and these corresponding positions represents 7 o'clock, which means the numerical in vector group symbol for this type of connection is 7, which will indicate the LV winding phase node voltage displacement with respect to HV winding phase node voltage, and that is given by the angle between minutes needle and hours needle. The angle between minutes needle and hours needle is 150 degrees, which can be written as 180 degrees minus 30 degrees. So these are the 4 possible connections of delta star connection, from which we got the 4 different phase displacements, that is plus or minus 30 degrees and 180 degrees plus or minus 30 degrees. Now let's know the phase voltage ratio and line voltage ratio, and we know that phase voltage ratio can be taken as equal to transformation ratio constant K, and which is same as that of single phase transformer, and that can be taken as equal to N2 by N1, where N2 is the secondary side number of turns and N1 is the primary side number of turns. So if small v2 is secondary side phase voltage and small v1 is primary side phase voltage, then the transformation ratio constant K can be taken as equal to small v2 by small v1. Now let's find out the line voltage ratio, which can be taken as equal to K or not. That depends on the connection employed in 3-phase transformer. So let's find out the line voltage ratio for delta star connection. Let capital V2 be secondary side line voltage and capital V1 be primary side line voltage. Therefore, line voltage ratio can be taken as equal to capital V2 by capital V1. Now observe the secondary side winding connection, which is a star, and the relation between line voltage and phase voltage for star connection is line voltage is equal to root 3 times phase voltage. So for secondary side, that is for star connection, okay, secondary side voltage V2 is equal to root 3 times the secondary side phase voltage. And coming to the primary side connection, which is a delta, so the relation between line voltage and phase voltage for delta connection is line voltage is equal to phase voltage. So line voltage V1 is equal to phase voltage small v1. So these are the voltage relations. Now let's replace the line voltages with phase voltages. So that will give you root 3 times small v2 by small v1. So that will give you root 3 times K, because we know that small v2 by small v1 can be taken as equal to transformation ratio constant K, and that is equal to 1.732 times K. So from this relation we can say that delta star connection can provide a secondary line voltage which is 73.2 times the primary side line voltage for k is equal to 1. In simple we can say that delta star connection can provide more voltage, that is 73.2 times the primary side line voltage. Therefore delta star connection is used for high voltage applications. Therefore the advantage of delta star connection is that used for 3-phase 4-wire system, because star can have neutral connection. Therefore we take neutral connection, and as this connection is having delta connection, so no distortion in secondary side voltage, that is no harmonics problem. And the third advantage is it can handle large unbalanced loads. These are the main advantages of delta star connection. And now let's see the disadvantages of delta star connection. And the disadvantage is that it can't be paralleled with transformers having different phase displacements. And the applications are, and we studied from the line voltage relation of delta star connection that secondary side line voltage is equal to root 3 times k into primary side line voltage, means delta star connection is used for high voltage applications. And the other advantage is this is mostly used connection, because on secondary side as it is having star connection, it can be used for supplying the 3-phase 4-wire system. Okay, so this is about star delta connection.